So once we understand the spatial relationships, we can perform spatial operations. So relationships tell us how geometries relate. Operations allow us to transform, combine, filter, or create new geometries based on those relationships. This is where a spatial analysis becomes a workflow. For example, we can create a buffer, um, clip data to a study area, and intersect two layers, and then join attributes by location or find optimal routes through a network. So let's go through the most common operations in this slide. Um, so as I mentioned, spatial operations transform geometries to produce new features and combine data sets and extract insights. So once we know how features relate, operations are how you act on those relationships. A buffer creates a zone around a feature at a specific distance. For example, we might create a 500-meter buffer around a school, or a 50-meter buffer around roads, or a 10-kilometer buffer around hospitals. And buffers are useful because many real-world questions are distance-based. Which buildings, for example, are within 100 meters of a flood zone, or which properties are near a transit stations, or which sensors are close enough to monitor an asset. So the important detail is coordinate system. If your data is in degree, buffer distances can be wrong. For buffers, we usually want a projected coordinate systems in meter. Another type of operation is called clip. So clip is like using a cookie cutter on spatial data. So we take one layer and cut it to fit inside a boundary. For example, imagine uh, we have a national road data set, but our project only covers Toronto. So we can clip the raw data set using the Toronto boundary, and now we only keep the roads inside our study area. So clip is useful because real data sets are often larger than our analysis area. So it helps reduce noises, reduce processing time, and keep the analysis focused on the geography area that matters. The next operation is called intersection. Intersection keeps only the area where two layers overlap. So this is very useful when we want to understand the shared space between data sets. For example, if we intersect parcels with flood zone, we can identify the exact portion of each parcel that is affected by flooding. So if we intersect land use polygons with a transit service area, we can calculate what types of land use are accessible by transit. So intersection is not just a visual overlay, it creates a new data set that represents the common geometry between layers. In this example, we have input coverage on one side, and then we have intersect coverage, and on the right side, we would calculate the intersection of the intersect coverage with the input data. The way that you can store and apply operation, um, we're gonna cover it in another episode. However, you can store the data and then apply operation using predefined operators in different platforms. Or you could develop your own from scratch, which we're gonna talk about it later on. So union combines geometries from multiple layers into one layer. The key difference from intersection is that union keeps all areas from both inputs, not only the overlapping part. And this is useful when we want to preserve the full geography from multiple datasets, while also understanding how their boundaries interact. For example, we might union zoning boundaries and flood zones to create a combined layer that shows every unique combination of zoning category and flood risk category. So union can create more complex outputs, but it is powerful for overlay analysis. The next operation in a spatial operation is called join. So a spatial join connects data from two layers based on location instead of a shared ID. So in a normal database join, we might join tables using customer ID, for example. In a spatial join, we can join a point to the polygon that contains it. For example, we can attach the neighborhood name to every building and assign each sensors to a city district or count how many incidents occurred inside each service area. So this is one of the most commonly used special operations because it turns geometry relationships into attributes that we can analyze and group and model. In this example, you can see how different layers uh, are joined together and you will see the result at the bottom. The next operation is routing. Routing is about finding paths through a network and the simplest version is shortest path. What is the shortest path or route between point A to point B? But in real applications, routing can consider many factors such as travel time, traffic, uh, road restrictions, turn penalties, vehicle type, slope, safety, cost, and so on. So this is used in navigation, in logistics, emergency response, public transit, and utility networks. And technically, routing depends on graph theory. So roads become edges, intersections become nodes, and the algorithm searches for the best path based on a cost function. The next operation is called nearest neighbor. So nearest neighbor finds the closest feature to each input feature. For example, for each accident location, we can ask what is the nearest hospital, or for each customer, what is the nearest store, or for each building, what is the nearest fire hydrant. So these sound simple, but at a scale, it becomes computationally expensive. If we compare every point to every other point, the number of comparisons grows very quickly, and that is why special indexing is important, and we will cover that later. Nearest neighbor is one of the foundations of accessibility analysis, service coverage, and location-based recommendation. The next item or the next operation is dissolve. Dissolve merge adjacent features that share the same attribute. For example, imagine we have many small parcels and each parcel has a zoning category. If we dissolve by zoning category, we can merge neighboring parcels with the same zoning into larger zone. So this is useful when the detailed boundaries are too granular for the analysis. So this solve helps simplify geometry and summarize data and create clear layers for visualization or reporting. The key idea is that we are not just merging randomly, we are merging based on a shared attribute.